Okay, we'll get started. So everyone, welcome to track 3. This is your introduction to Windows 32 shellcode. So if that's what you're looking for, you're in the right place. I mentioned earlier, if you play Overwatch, you might recognize many of the GIFs that I have in the talk. Otherwise, just enjoy the pretty purple GIFs. Just a quick introduction for myself. My name is Maddalena. I'm a senior security consultant for GuidePoint Security, where I do red team stuff, penetration testing, social engineering. None of what I'm really going to talk today necessarily has a whole lot to do with my job. It's just kind of a passion of mine. I got interested in it while working through my OSCE, and by no means am I an expert on anything I'm going to talk about today. So the goal of today is to help you learn from what I learned while trying to teach myself assembly and writing my own shellcode, and try to give you a path of where to get started and where I felt I didn't stumble, that I actually hit upon things that learning really helped me out, and to help you all get started down that path. I have my Keybase link down here at the bottom. You can find me there as a C Maddalena. I mention this primarily because when you go there, you can get the link to my website, a link to my GitHub, a link to Twitter, all right there in one place, other than me trying to give you a bunch of usernames. On my GitHub, all the code I'm going to talk about today is available, so all the assembly, all the Python you can find there. If you go to my either my Twitter profile, I have it pinned as a tweet at the top of my profile, or go to my website, you can find a very in-depth technical write-up of the TCP stager that we're going to talk about during the talk. So if you're interested in how each one of those functions gets called and how everything was put together, it goes into a much more detailed explanation of all that we don't even have time for, and you'd probably all fall asleep through if I tried to put you through 50 minutes of that. But that is available should you be interested. So our agenda today is we're going to be dealing with Intel x86 architecture, and we're going to be dealing primarily with targets that are Windows 32-bit VMs. The reason for this is, yes, there's 64-bit, there's Linux, there's other architectures, but I find that it's much easier to start out with this if you have a narrow scope. So targeting Windows and Intel x86, you have some instructions available to you that make things a little bit easier, and the basics you learn, that we're going to talk about today over the next 45 minutes, and that you learn from writing shellcode for Windows, easily carries over to Linux. It makes transitioning to 64-bit pretty easy. You'll have some learning curves for instructions that aren't available to you, or new instructions that become available for things like ARM and other architectures, but that all comes as you move around and get deeper into the topic. So speaking of topics, what we're going to talk about today, I'm going to go over a couple of just the need-to-know basics, kind of do a quick review of your computer science class you probably had back in college. Then we're going to discuss actually how you can debug shellcode using Python, which I think is actually kind of my favorite part of the talk, because I think it's a pretty neat solution, way easier than some of the snippets of C and things like that you can find online. Then we'll actually start getting into some shellcode and doing comparisons of automatically generated shellcode versus shellcode we can write ourselves, and why you might want to bother writing your own shellcode versus just using MSFN. So before we get started, just to set a baseline of what it is that we're talking about as far as shellcode. It's a pretty ambiguous term. It's, it refers to code that gets us a shell. So we call it shellcode. But it can do a lot more than that, and there's a bit more going on underneath than just the blob of hex that you often see in exploit scripts, or that MSFN spits out for you. At its heart, it's a bunch of assembly instructions that get compiled and formatted into what we call shellcode. And the key thing that I want you to keep in mind as you're learning how to write shellcode, and as we talk about this for the next, half an hour or so, is that these are instructions that are often written to be injected into an already running process. So this can work for and against us. So that when you're injecting shellcode via an exploit into a running process, you get to run as, for example, that process is running as a privileged user, you get to run with those privileges. If it has loaded Windows libraries, you get to use those Windows libraries. But the reverse is also true. If it's a low privileged user or those libraries haven't loaded, you're going to have to deal with that yourself and figure out new ways, to accomplish whatever it is you're after. But of course, there's also the other type of shellcode. That might just be a portable executable you put on a web server, or you send in a phishing email that is meant just to kind of be detonated on a system as a standalone thing. We still often refer to that as shellcode, even though then you have to have sometimes extra steps of loading libraries and doing a few other things. So always have a plan is really what I'm trying to get at, is understand what is your target, what are you trying to do with the shellcode, what is its purpose, and work from there, because there might be certain limitations you have to deal with. So getting into our basics, we need to talk a little bit about memory and registers. So when it comes to CPU registers, there's quite a few of them. There's 8 for 32-bit. You get up to 16 for 64-bit. I encourage you to go and look up the architectures and see what their common uses are. But really, for today, just look at CPU registers. We can use them however we see fit. However, there are a few things to always keep in mind when we're dealing with registers, because we're going to have to manage them very carefully and plan things out if we want our code to be efficient, and we don't want to keep stepping on our own toes. So I want to call it just 2 registers here we're going to look at pretty often in our demos today. The first one is ESP. This is the stack pointer, hence SP for stack pointer. This is just really handy because it's always going to point to the last thing we put into memory. So if we need to make a pointer to something, we put it into memory, and we can save the value of ESP to create our pointer. ESP is always going to be pointing to that top of the memory stack. EAX this is the accumulator register, and this register is often used for like math. You can put a value in it, and then add to it, subtract to it, take another value, add to it, etc. But its key thing that we want to keep in mind is that especially with Windows, it also has the return, whatever like the return codes or whatever is being returned by a function goes into EAX. So if we're calling a function, but then we're about to turn around and use EAX to do a calculation, we might end up stepping on our own toes if we're not paying attention, because we might destroy a return value that we expected to be able to use later on in another function or something like that. So being mindful of what each register does and how to manage them is incredibly useful, and it's just a skill you'll pick up as you start working with situations where maybe only certain registers are available to you, or you're working with certain functions and things are changing. So looking at the memory stack now, when you hear references to the stack, this is just a section of memory where our data is going to go. So when we put something into memory, like a string or a command we want to run later, then that's going to go onto the stack. And the key thing to remember about the stack is that it builds upwards, which is just think about you're building like a tower out of blocks. You have to put one block down first, and then you can keep building it up. If you want to take that bottom block out, you have to take every other block on top of it off first. So that's where we get into push and pop. These are our Intel x86 instructions that let us interact directly with the stack. So push, when we push something, it goes right on top of the stack. It always goes on top. It doesn't go somewhere in the middle or anywhere else. It goes on top. When we pop something, we pop the top thing on the stack off of it. It's pretty easy. A couple of things to note about pop is that we can just call pop, and it'll take the top thing off the stack and throw it away. If we say like pop EAX or give it some other register, it'll take that value and put it into that register. So we're going to use push and pop a lot to set up function calls, put something into memory to use later. These are functions we come back to quite often. The last thing we need to worry about with memory is endianness. So with Intel x86, we're going to be dealing with little endian, which is just the sequence of bytes it's the order of the bytes that we're going to be putting into memory. So just to give you an easy example, if we're going to be pushing, say, the string boop to the stack, we have 4 characters, and 32-bit we push our strings as 4 character pieces. This is just 4 characters, so really easy. Our first step is just going to be converting it to hex. So when we convert it to hex, we have just 42, 6F, 6F, 70. And note that that P, that lowercase p, is a 70. When we're going to do our assembly instruction to push that onto the stack, we push, and that P comes first. So where this might get a little bit confusing, because that's pretty easy. Just remember, reverse everything. You're fine. Do that with memory addresses. Do that with strings. But the key thing to remember here is that if you, for some reason, then want to go into your code at the end, like your shellcode, and make an edit because, oops, I have a typo in my command, and rather than recompiling everything, I just want to make one little change, you're not going to find that sequence of 70, 6F, 6F, 42 in your shellcode. You're going to find 68, 42, 6F, 6F, 70. 68 is a push, and then you see that our string comes back around into the correct order. So when we're dealing with endianness, that's what we're dealing with when we're writing our assembly, or we're looking at something in a debugger for the actual instruction. If you're then looking at your shellcode afterwards, like in your exploit scripts, just be mindful of the fact that that's not incorrect. Don't flip them back around. You'll just break things. And finally, just to wrap up the basics, there are ways to protect memory and a couple of things to keep in mind. We're going to be working with Windows addresses today, and if you hard code an address for a function for Windows into your assembly, it will not work on other versions of Windows, because actually those addresses tend to change between even different service packs. Even some updates might change them, and they'll definitely change between Windows versions, like from XP to Vista to 7. and we'll talk about that a little bit more later. And then there are ways to protect memory, like address space layout randomization and dep. These are things that can be defeated, and if you get into exploit development, you can start working around them and figuring out ways to defeat them. I just wanted to mention them here so you're aware there are ways to try to start messing with shellcode to keep it from working on certain systems, but that will be beyond the scope of what we're going to talk about today. So let's start talking about how we can test our shellcode. So we write some shellcode. If you go Google around online, like, hey, how can I run my shellcode to test it? You end up getting a lot of like little C snippets and things like that, which are fine. But I actually like to use Python, and I think this is a pretty neat way to do it. So the first thing is we need to take our assembly. We'll compile it, which is really simple. It's compiling assembly can kind of something that's going to be complicated, but you can just use NASM. I mean, it's already pre-installed on like a Kali VM if you have it. And you just give it your assembly file, and it'll output a bin file for you. That bin file is going to contain, you can look at it in the hex editor, it's just going to contain all the hex, all of the machine code for your assembly. And then what we need to do to be able to have it run in like an exploit script or in our Python debugging script is we just need to convert it to escape all that hex with that little /x in front of it. So effectively, you're just replacing all of the spaces you would see in a hex editor with \x. So please, script that out. There's tons of scripts available. I have one on my GitHub you can use. You can find them, like the Corlan exploit writing series uses a Perl script. They're out there. It'd be really tedious to do this by hand. So just script it out, and in the end, you'll have your a string you can drop right into like a Python script and have it run. And to do that, you can use Python C types. And this is a really cool little library. It just lets us run like assembly instructions as our shellcode right like on a system with Python installed. So we just give it the shellcode as a byte array, and it runs. And the other really cool thing is that we can actually import libraries. So if, for example, like we talked about earlier, if we're expecting that, hey, we're going to inject this into, a running process, that we assume we'll have the Windows socket API already loaded. Python's not going to load that for us by default. But we can tell C types, hey, please load this DLL for us into memory so that we can create and kind of curate an environment for our shellcode to run in. So we can make sure that we might take things away, add things, and just see if that changes our shellcode or if we can do different things for experimentation. And this is really what that looks like. And as far as the debugging purposes, this is what I want to call attention to. This script's available on my GitHub, but it's also just out there if you look for Python C types and running shellcode. But there's just a couple of spots here. This little breakpoint here, the /xcc, is a breakpoint that's commented out. And then I have this little debug prompt. And I'll actually show you how this works later, but just to give you a quick rundown, is I always put the little breakpoint at the start of my shellcode there, and I can leave it commented out when I don't need it. But if I uncomment that, and then I run this script, Python will prompt me to hit enter before it'll continue with the shellcode execution. That gives me plenty of time to load up Immunity or whatever your favorite debugger is, attach it to Python, and then you can let it run. It'll hit that breakpoint. Your debugger will pause and say, hey, I've hit a breakpoint, take a look at this, and there's your shellcode right there. All this is, you can see it there as all the assembly instructions ready to go for you to review to make sure everything looks right. You can step through it in the debugger to make sure everything is going to the stack properly, etc., and see how everything's working. It's actually pretty slick once you start working on it, way better than just like dropping blobs of shellcode into a C file, compiling it, and hoping it runs. So if we're going to start debugging some shellcode, let's actually talk about generating some shellcode that we can take a look at in a debugger. So, of course, there's the easy way. We can just use like MSF Venom. You can go to ExploitDB. You can download shellcode samples. There's tons of ways to get samples of shellcode that you can drop into a script and have it run. They all work. They're fine. But then we can have the hard way. We can just write it ourselves. So the question is, why would we then ever want to bother writing it ourselves? So there's a couple reasons. If you've seen me give talks before, I talk a lot about like tool development. And usually my message is, well, you can write a tool that even if it's not very good, at least you've learned something probably along the way. Take a look at your tool, tools that you're using, see how they work, what commands are they running, so you can have a better understanding of that whole process. It's the same thing with shellcode. Even though maybe you're not going to write anything really advanced or crazy, even just writing your own like little things, and we'll take a look at an example here on the next slide of just a very basic function you can call with assembly, you'll at least have a better understanding of how this is all working and what MSF Venom is doing. And then also, once you start building that skill set up, you can actually start taking advantage of it in different interesting ways. Like, for example, you can write custom shellcode. You could go and write something really crazy, totally custom, and use it. But also, it might just be helpful to be able to make smaller shellcode. Because the way MSF Venom works is it pulls from a whole bunch of little pieces of assembly files. It knows how to stitch them together and edit them on the fly and outputs your shellcode, which is why if you tell MSF Venom to output a certain payload for you, it's very consistent, which is great. But it also means that if you need smaller shellcode, because like your memory buffer for an exploit is only 100 bytes, and you're getting 150 from MSF Venom, it's not going to get smaller if you run it 6 times. You're going to get that same payload 6 times. Great for consistency, not great if you're in a bind where you need smaller shellcode. But you might be able to write it yourselves. You might be able to better target that shellcode and make it much, much smaller. So let's take a look at how that might work. So just taking a very basic MSF Venom payload, just making a message box pop up with a caption and a title. If we run that through MSF Venom, we get 252 bytes, which seems kind of big for just calling one function and with a couple of strings. So the first thing we got to do if we're going to figure out how this is working and how MSF Venom is doing this is we're going to have to go to MSDN. And with Windows Shellcode, you're going to spend a lot of time on MSDN. It's your best friend. You can go there. You can see all the documentation for all the Windows API calls. So here's the one for message box. So first thing we notice there's actually 4 arguments rather than just the 2. Okay, so that those were kind of hidden from us with MSF Venom. And if we look through the documentation on MSDN, we learn that there's also a couple other things we need to know. For one, our text and caption, it doesn't want ASCII text. It won't run with just the text. It actually wants pointers to those. So that's just an extra step we're going to have to add in there. And then the other 2, the HWND and the UType, those are who owns that message box. We don't really care, so we can set that to 0, just nobody owns the message box. And then the type of message box, because Windows has like OK cancel, yes, no. We just want a basic OK message box, so we can give it a 0 as well. So there's a couple more things we're going to have to add to that function. So now that we know what we need to do, we can actually write that out in assembly. So we're going to, in my examples, I'm actually going to target a VM I have for our demos, just a Windows XP Service Pack 3 VM, so we can hard code the addresses. And I want to call out a couple things here. For one, you can see here at the top, we'll start off by XORing EAX with EAX. And if you're familiar with, XOR in any capacity, you'll know that if you XOR something against itself, you always get 0. So this is just a nice trick when you're writing shellcode to be able to get 0 into a register, where normally if you tried to, we could very easily just say, hey, move 0 here or push 0 to the stack. Except when we're talking about shellcode, again, if we're expecting this to be injected into a running process via an exploit, null bytes are typically very bad because they are string terminators, which is why we're going to push that 0 to the stack with that second instruction, because we need to terminate our string. Because if we don't terminate strings, when the computer is reading, say our caption for our message box, it will just keep reading everything from memory until it hits a null byte. Which if we're trying to run a command, could be really bad if it just starts reading a whole bunch of junk from memory until it hits a 0. So we need to terminate strings. We need to have null bytes in our shellcode, but we can't put them into our shellcode. So the way we get around that is we make the computer push like null bytes into registers for us via tricks like XORing a register against itself. So what happens here is we make that 0, we can push that 0 to the stack to terminate our string, and then, the move, the MOV, ECX, ESP. Again, we had that ESP register we talked about earlier. ESP is now pointing to the, what we last put into memory, which is our string for our caption. So we can make a pointer from that very easily. We repeat the same thing for our second string. And then we can push our arguments for message box. So we push our 0, caption, text, 0, and then we call the message box function to make the message box show up. Cool. It's pretty easy, and that actually comes out to just 39 bytes of shellcode. So way, way smaller than the 252 bytes. But before we start saying, like, well, what on earth is MSF Venom doing? Why is this so much smaller? We need to start looking at what else is MSF Venom doing by default. One of the things it'll do, especially if you've ever used like a Metasploit module, you might have noticed that like exit function parameter you can set. So what that does is you can tell it to say like call exit process, call exit function, or call exit like thread. So we'll call exit process. And what this does is it just tells Windows, hey, we're going to close down now, and everything is fine where there was a problem was encountered. So we're just going to say we want to call exit process with a 0. Just to let Windows know that when you click OK on that message box and it closes, in our case, it'll look like Python just died because the thread just ended. So Windows will think it crashed. So if we say exit process 0, it just lets Windows know, hey, everything's fine, it closed as we expected. That'll add another 9 bytes. but we're still way smaller than 252 bytes. So let's just make sure this actually works as we expect, because maybe we're missing something. Let's pop over here to our Windows box, and I'll show you a couple things. So here's the script we took a look at earlier. Whoop, why is that not? Maybe I need to stop the slideshow. There we go. What? You know, you have an offline demo, and it should work, but then Mac OS is going to screw me. All right. Wait. There. Fine, we'll do it this way. So here is our test script that we have. So this is just the C-type script. And you can see here we have like a breakpoint here. Here's a shellcode we'll take a look at earlier. But here's our message box shellcode. So we'll just take that and leave that as a shellcode variable. And like I said earlier, you know, we can just drop this in as this is what our shellcode ends up looking at with that /x formatting. And so all we have to do is run it. And what I wanted to show you, and maybe I can show this to you later if I can fix this, but I would show you how the debugging works, but that's going to be really difficult as this. So I'm just going to comment that out. And now, if we run the script, we get that debug pause. At this point, we could attach immunity to this, and then we could let that breakpoint be hit, and then step through all the shellcode. But we'll do that. We have our sound there. Oh, goodness. There it is. So we have our message box pop up. So everything is working as we expected, but our shellcode is still much, much smaller. Let's go back, and since it's not going to pop up on my main screen, there we go. Why is this not? Sorry about this. I don't know why it's doing that. Is there a shortcut, Victor, or does anyone know of like a shortcut to switch the presenter slide back? Because it's not even giving me the prompt. Oh wait, I can. This is the worst. Yeah, success. All right. So just taking a look at our results here. Obviously, they're both going to do the same thing. I'm not going to bother trying to show you like the MSF, Venom shellcode. We know it's going to pop up a message box, but so did ours. So why did my 48-byte shellcode do the exact same thing as 252 bytes of shellcode? What are they doing different? Well, primarily, the big difference comes from the fact that MSF Venom shellcode is by default will always run across like pretty much any version of Windows. So it's going to do a couple of things like actually dynamically loading the addresses of the functions you're going to need at runtime. And so that's really cool. You can do that. It's very useful. That'll make your shellcode much more flexible. The downside is kind of significant in that you get that much larger size increase per function call. So that's why if you ever look at like the size of a like an unstaged like MSF Venom payload, it's huge, because it has to go and dynamically resolve a whole bunch of functions. But here, if we actually just hard code the addresses, it works out way better. We get much smaller shellcode. So this is what we were talking about earlier. Let's say if we had an exploit and we're like, well, we know it works, we can get code execution, and maybe you, at the very least, you don't have to make anything crazy. You just want to prove a concept that it works. You could put together something that runs a command using system or WinExec, makes a message box pop up that proves code execution that is way smaller and fits into that buffer without needing to rely on MSF Venom. So let's talk about building something a bit more complicated, like a TCP connect back stager. So this will actually require several more function calls in the correct sequence, and it will require a bit more planning on our part. So just in case you're unfamiliar with how a stager works, this is you probably used one if you ever messed around with Metasploit, kind of like the default go-to, payload is meterpreter / reverse TCP. That / means that it's a staged payload. Meterpreter / means it's staged. And what the stage does is we're going to send a smaller payload to have it executed on our victim machine. And what that does is it just sets the stage. It puts together a buffer for us that it's going to then connect back. In this case, we're going to do a connect back stager. So it's going to connect back to the attacking machine and get more shellcode. It's going to get some stage 2 shellcode. And it'll create a little home for it back at the victim machine that is probably going to be much bigger than the initial buffer we started off with. So it connects back home, and the attacking machine sends back the stage 2 shellcode, and it gets executed. So if we go over to MSDN, we figure out, okay, well, what do we need to do to make that work with Windows? So pretty easily, we find out that, okay, we're going to have to use the Windows Socket API because we need a socket. We need to be able to connect back. So MSDN will tell us that for WinSock, we're going to need the WinSock API loaded into memory. But if we're attacking a network process, again, remember, going back to knowing what it is we're attacking, we know that, okay, if this is like an FTP server or something that we're attacking remotely, it's going to have network processes and it's going to have already initiated WinSock. But let's just say it's not, because in our case, using Python, it's not going to be initiated. We know we have to call WSA startup. And that allows us to create a socket, allows our process to request a socket from Windows. Then we can call WSA socket, which actually requests that socket from Windows. At that point, that socket's worthless. It doesn't really do anything until we set it up. So we have to call connect and receive, and that sets up the socket to allow it to connect to something, and then allows it to receive data. And that's really what goes into it. It seems pretty simple, but we're going to have to do a lot of like juggling of registers and setup to get this working. And I would love to walk through all of it and show it to you, but this is where that blog post will come into play. It goes through each one of these functions. So for now, I'm just going to highlight one of the functions, the socket function, because it is a pretty good example of how we can work through something and plan it out. So in this case, we go to MSDN, we take a look at socket, we see we need 6 parameters. But if we look over the documentation, we see that everything from protocol on to those next 3, we don't really need them. There's like flags and protocol types we can set, but we don't need them for this. We can set those to 0. And then if we look at type, this is the socket type. We're going to do type sock stream, which is like a streaming socket or TCP. And that's a type 1. And then we're going to go into address family. And that's the very first parameter. And we're going to do it with address family 2, because that's address family INET, or internet address, or IP version 4. So we plan that all out, and we look at them and go, actually, so we're just going to call WSA socket 210000, which actually, now that we know that, makes planning out the assembly really simple. Because we can do all that with just this. We set a register to 0, and then we push a bunch of zeros, and then because we just need 1 and 2 in that order, we can do something as easy as increment that same register to 1 and push it to the stack, and then we can increment it again and push it, and now we have a 2. Works out really easy, then we call WSA socket and we're done. So by planning ahead a bit and looking at that MSDN documentation, we're able to plan out our stager a bit more carefully and have it work. So we're going to try another demo. So let's see if we can make this work. So we'll start off with our Windows XP demo here. So my stager shellcode is up here up top. So we're just going to change this back to like message shellcode. So the nice thing about this script too is because you can just set a whole bunch of samples to shellcode, and you can change the variables and just leave the one you want it to actually run set as shellcode. So in this case, here's our stager shellcode. And so we're ready to go there. And all we have to do is run it. So now it obviously hasn't executed yet. So we're going to come over here, add a second VM, which is a really fun, comfortable demo for me. And of course, I made this really big so you guys could see it. And now in this view, that looks ridiculous. So All right, so a couple of things to note. Oh, we didn't. You think I'd be able to type sideways onto a projector, okay? Oh, demos. But it'd be helpful if I can remember the name of my directories. So we have a couple of things in here. Encoder.py is the encoder that I talked about earlier from my GitHub. And then here's our message box. So I'll show you this. Here's our message box assembly from earlier in the assembly file. And just a quick note, like you can find this online, but really it's just, you're going to write out the assembly. The only thing that makes a difference is we just need to add that to the top for it to compile properly. And speaking of compiling, we'll compile this real quick and actually use it with our stager. So we can just name this, messagebox.asm. Oh man, this is tough, guys. There we go. What? Oh my gosh. It's not like this is being live streamed or anything. It's fine. So, if we take a look at that in the hex editor, there's our machine code, there's our raw bytes, and that's actually all we need for this. So our stager is going to be connecting back on just port 4444 on this IP address. So we just set up our, forgot the L. There, so we set that, and then actually we just need to pipe our payload in there. And since we already have this as raw bytes, this is compiled, ready to go. Okay, fine, we'll do this the hard way. There we go. So now there we go. And it triggered. So just to prove that I didn't just run the same shellcode again, we can come back and we can see here that we did have a connection back from our VM. So the stage 1 triggered, came back, it connected back to the other VM, collected the new shellcode, and executed it. So cool. So we can do something a little bit different, because we already know that our message box shellcode was pretty small. So we can actually use an MS Venom 1, and let's just do something silly like Windows speak pwned. This is the one that uses the Windows speech API to say you've been pwned. So command looks right. So let that run, and we'll get actually a significantly larger payload, 247 bytes. So we'll just set up that stager again, and this time we'll send a much larger payload over. Run it again, and hopefully we'll be able to see this, because I know last year we had audio hookups, but hopefully this will be loud enough for you to hear. Actually,
you got pwned.
So there, so it triggered, and yeah, and just as kind of an aside, you see this is what would happen if we don't call exit process, which I think for such a ridiculous payload, MemSFM doesn't even bother adding an exit, an exit function to it. But there you go. So let's try to get back to the slides. All right, so a couple of just notes and resources for you. So fuzzysecurity.com has some really great exploit writing tutorials. Specifically, module 6 actually is where I got the inspiration for the whole message box and MSFM comparison. FuzzySec does a really great job of walking through those, and as well as a couple other things that I hit on during the talk, but it's all documented there, like making sure that your strings are broken into 4 bytes and etc. And he does some really good comparisons. Just that's a really great module, but the whole exploit development series is really great if you want to get into exploit development. Corlan, of course, has a similar excellent series. It's much wordier. It's a bit more of a sit down, and I'm going to read this for about the next 50 minutes rather than FuzzySec's much more kind of bite-sized, easier to get through modules, but obviously full of really great stuff, totally different examples, etc. And then, of course, I would be remiss not to mention, Scape's Understanding Windows Shellcode paper. That's where actually a lot of the pieces for the stager shellcode, kind of came from and helped me complete that. It's not really one you sit down and read. It's just more of one that is very handy to have as a reference to, I want to build a stager, so I'm going to go look at the stager section. And then Hacking the Art of Exploitation. This is a really great book for getting started with like assembly and learning, all of the kind of ins and outs of some of that lower level part of the exploit development and writing shellcode. It is a very tough read if it's a brand new topic to you. It literally put me to sleep several times. I actually I did a lot of my own research and eventually came back to it and tried it again and had a much easier time reading it. So it's one of those things you might buy it, try it out, see if you can get through it. If you can't, maybe come back to it later. But it does a very good job explaining everything. It's just, I know at least for me personally, it was hard to get through until I had hands-on experience and learned it a bit better myself. So due to technical complications with those demos being a lot shorter than I had planned, I think we have time for some questions. Anyone have any? All right. Oh, yeah. Oh, yeah. So there is. So the question was, what happens when the stager pulls in the shellcode? How does it execute that shellcode? So what happens with the receive function, which is the last one that gets called, is that'll set aside a chunk of memory for whatever size you tell it to for that incoming shellcode. So then what happens is it's just going to shove that into the shellcode, or it's going to shove the shellcode into that section of memory. So like basically the very last function of the stager example that I have, and like if you see it on GitHub, is a jump EA. I think I have it set to. I think it's I'm using EAX as the register for that start of that buffer, but it's a jump to that section of memory, which means that the CPU is going to return to that as the next instruction to run, and that's going to be the shellcode. So it'll jump to that section of memory and then execute what's in it. Yep, so it starts off, you create the socket, you tell it to connect back to the attacking machine, and then it connects back, it runs receive to wait for data coming back, and then it puts whatever it receives in memory at an address that you now know because you put it there, and then the very, very, very last step would be to now go to that address in memory and execute it. Yes? So the question is, why did I use XP? Not really. It was just what I had available at the time, and I had the addresses available. I have since set up some additional VMs for my lab, but just in this case, it was the examples are ready to go, already written for that. But yeah, I mean, the same thing would work on other versions of Windows. Just obviously in these particular examples, because I've hard-coded the addresses, you would have to update the addresses, but they would work on Windows 10. Oh yeah. Oh, he mentioned that also you would have to start competing, worrying about perhaps like ASLR and DEP on later versions of Windows as well. Any other questions? All right, thank you very much, and thanks for hanging with me through those technical difficulties.